Hello everyone, I am Miss Hu, your physics teacher. Or to some of you, I'm your science teacher. Now, what we'll be learning in this video are about components in a circuit. This video is meant for my Year 7 science students, but I'm sharing this on my YouTube channel because this is a fundamental topic in the electricity concept, so this might benefit some of you who are new to this topic. So the aim of this lesson is to enable students to be able to describe how current is measured, to describe a rule about current in series circuits, as well as to describe what happens when you add or remove components in a circuit. So here's a little joke for you. Yes, do not be like this guy. In case you're wondering what's wrong, this is a shower in a bathroom, and this is the circuit breaker, which is basically electrical fuse box. Bad idea. So now, anyway, let's get to the lesson. But before we go into that, just to let you know that because this video lesson is meant for my Year 7 science students, we will be going through how to fill up the blanks in the notes of the booklet, which I have already printed for my Year 7 science students. Now, even if you don't have the booklet, you might find this video still quite educational. If you would like to know more about the booklet or worksheets that I usually prepare for my students, do drop a comment and I will share updates on my website, physicsrocks.com. For now, let's get started. So we are now on page 16 and we're now on topic 4, components in a circuit. So first we're going to start with how to measure current. Now for the components which we use to measure current, but some of you may not have seen a component yet in real life. Now for my students who have not yet had the opportunity to observe or set up electrical circuit in class, we will do that in an upcoming lesson. For now, let's learn in theory first. So the device that's used to measure current is called an ammeter. And this is a typical ammeter that is used in the school labs. Now, depending on the apparatus that you have in your school labs, it may look slightly different. Some of you might even be using digital ammeters. It doesn't matter whether it's an analog or digital ammeter, they're all used to measure the same thing. They're all used to measure current. Symbol here refers to how we're going to draw this device in an electrical circuit diagram. So if you can recall, an ammeter is quite simple. It is quite simply a circle with the letter A in it to represent the word ammeter. Remember that the letter must be a capital A. And we have lines on either side to represent the connecting wires. Current is measured in ampere, or some of you might call it amps for short. The symbol, meaning the short form of the unit ampere, is A. So if you're wondering how to use A, it's similar to how the short form of centimeters is cm. For example, when you measure length, and let's say the value is 10 centimeters, you would write it out as 10 cm. So the same thing for current. If the current value is, say, for example, 10 amperes, you write the short form of amperes as capital A. So you'd write 10A. So this is the name of the device that's used to measure current and the unit that we use to measure current. Let's take a look at some of the common values of current that flow through our devices. So for those of you who are using your iPads, you'll find generally that the iPads would use a value of about 2 ampere of current. Air conditioners are much higher powered machines. They need to be able to cool an entire room. Therefore, they use a lot more electrical energy, which is why they have a much higher current usage. Depending on the type of air conditioner, most air conditioners would use up to 12 ampere of current. Water heaters also use quite a lot of current because they need to heat up the water very, very quickly. Water heaters may use up to 19 amperes of current. Now, you've also heard of electric shocks or electrocution, right? So what kills a person is not the current itself, but the fact that the current can actually stop the person's heart from beating. And our heart is a very sensitive organ. So yes, a very low amount of current is all it needs to stop the heart from beating, as low as 0.01 ampere of current. Now, I know you're looking at this and you're very worried. Oh my gosh, what if we accidentally touch the wire and there's current flowing through us? So what you should know is that the human body is sort of like an electrical conductor. Current can flow through the human body, which is how a lot of basic devices work. For example, the weighing machines that are used to measure your body fat and your muscle mass, they use small values of current that flow through your body. Even things like your smartwatch that are able to measure your heartbeat also use a little bit of current in order to monitor the human body. So in case you're wondering, then how much current is actually flowing through our body? So the important thing here, in addition to the value of the current that flows through the body, is where the current flows through. The current can flow through anywhere in your body. It's just that if the current flows through the heart, it's able to stop the heart. Now, don't worry, all these devices are built well in such a way that the current will not flow through your heart. The only way that current can be forced to flow through your heart is if it's a lot of current that's too random, for example, a lightning strike or electric shock that forces the current to flow through your heart. So even when current flows through your heart, it has to flow through a certain way to make the heart stop beating. So don't worry, it's very difficult for current to flow through your heart. But if the current doesn't flow through the heart, some people can even survive electrocution. So that's how sometimes you hear of how people are able to survive lightning strikes. That's a huge amount of charge there, a huge amount of current. But a person can survive a lightning strike if that person is lucky enough that the charge from the lightning strike did not travel through the heart. So whether it travels to the heart or not, it really depends on your luck. We'll go through the discussion of lightning strikes another time. Let's move on with the lesson. Current in a series circuit. Now when it comes to circuits, there are many ways to arrange the components in a circuit. The important thing though is that if you want to make sure that current can actually flow through the circuit has to be closed. In terms of arrangements, you might hear of series and parallel circuits. Now for year 7, we're only going to focus on series circuits. I'm not going to go through parallel circuits for this lesson. If you would like to know more about parallel circuits, I'll put that in a separate video where I will discuss about series and parallel circuits in detail. For this lesson, let's just focus on series circuits. In case you're wondering what does series mean, series means that we arrange all the components that we have in our circuit in a series. That means one after the other, very neatly like this. So we have the cell here, we have ammeters, and we have lamps, all arranged neatly one after the other. In reality, of course, you might place the ammeters and lamps randomly, but what makes it a series circuit is the fact that the wires are connected all in one loop like this. An important thing that you must understand about how current flows in a series circuit is that the current in a series circuit is the same throughout the entire circuit. Now, as you have learned in an earlier lesson, current flows from positive to negative. As we have already learned in a previous lesson, when you look at the battery here, you must be able to identify where the positive terminal and negative terminals are. So the long line is positive while the short line is negative. So this side is positive and this side is negative, which means that current is flowing anti-clockwise in this diagram. So the arrow I've drawn over here represents the direction of the current flow. Now as you can see, there's only one track for the current to flow. So you can imagine as if there's only one road for the current to flow. Imagine you are one of the charges that is trying to travel from the positive to negative terminal. So if you are here and you're trying to get through to the other side. Now remember, you can't jump directly from here to here. Imagine there's a huge fence that you cannot climb. So you have to go through this track. So when you start here, you got to run along this line. You've got to go through the first ammeter and then the first lamp, second ammeter, second lamp, third ammeter, third lamp, and then fourth ammeter before you're finally able to reach your destination. So here, there's only one track. So because you can see there's only one track, what happens is that for current, the current will end up flowing at the same rate throughout the entire circuit. And that's why in a series circuit, the current is the same throughout the track. So we've got 4 ammeters here. If one ammeter shows a reading of 0.3 amperes, all the ammeters must show the same value of 0.3 amperes. Now, if the current value changes, and let's say one ammeter it has increased to 0.5 ampere, then all of the ammeters will show the same value of 0.5 ampere. If at any time you set up a series circuit and one of the ammeters shows a different reading, that means that's an anomaly. There's probably something wrong with that ammeter, or the ammeter was not calibrated properly. So if current on one side of the circuit increases, all of it would increase. If the current decreases, all of it would decrease. The current throughout the entire circuit will always be the same in a series circuit. Now for the next section, We're supposed to do an experiment, but obviously in this video lesson, we're not going to be doing the experiment. So for my class, if we haven't done the experiment yet, we will do this in the future. For now though, let's learn this in theory because it's actually very logical when you think about it, and this will enable you to answer any questions with regards to this kind of situation. So what do you think happens to the lamp if you add another lamp or add another cell? So now on this slide, I'm just going to draw the circuit symbols to make it easier for me to draw this out. Also, you should be getting used to circuit symbols when it comes to drawing or recognizing circuit diagrams. So let's say we have a very basic circuit where we have one cell and one lamp, like this. Now, when we connect it this way, the lamp would light up with a certain amount of brightness. Remember that the cell is providing electrical energy and the lamp is converting that electrical energy to light energy. If we were to keep the number of cells the same, but we add more lamps in series like this, what do you think is going to happen to the lamps? Are they going to shine with the same brightness as the first circuit? Think about it. You have only one cell in each circuit and the cell is providing electrical energy. So in the first circuit, one cell is providing electrical energy to one lamp. But in the second circuit, we have only one cell providing electrical energy, this time to two lamps. So that's right, the electrical energy now needs to be shared between two lamps, which means that the lamps will not be able to light up as brightly as the lamp in the first circuit. So can they still light up? Yes, but probably not as bright. Now, just to let you know, the ratio is not necessarily half. Don't think that, oh, one lamp to one cell, one lamp to two cells, the lamps are now half as bright. The calculation is more complicated than that. For now, you just need to know that the lamps will now be dimmer. How much dimmer? You don't have to specify. So we're just going to write here that the lamps will be dimmer. Now, what if we keep only one lamp, but this time we put two cells? So think about it. If you have two cells, what happens to the amount of electrical energy that's being supplied to the lamp? More, correct? Which means that the lamp will now be brighter. Again, don't assume that the brightness is double. Calculation is more complicated than that. You just need to know that the lamp will be brighter. So it's quite logical, right? You just need to remember that cells provide electrical energy. So the more cells there are, the more electrical energy is provided. If you have more bulbs, then more electrical energy is required because each bulb needs a certain amount of electrical energy to be able to light up to that particular brightness. What if we put two cells to two lamps? What do you think about the brightness in this circuit compared to the first circuit? That's right, the brightness would be the same because now the ratio is back to the original, one cell to one bulb. So we've got two cells, two bulbs, the ratio is now one cell to one bulb. So yes, this would have the same brightness as the original circuit. I've written here same brightness as circuit A, and I've labeled this as circuit A just to make it clear for this particular slide. This is true not only for two cells and two bulbs. You can put three cells, three bulbs, four cells, four bulbs, and so on and so forth. The ratio can also be played around with. Say for example, if you put three cells to two bulbs. Now, compare this circuit to circuit A. Do you think the bulbs in here will be brighter, dimmer, or have the same brightness as a bulb in circuit A? So you do need to look at the ratio. Remember, this is a 1:1, this is 1:2, this is a 2:1. Here's a 3:2. So which means that these three cells have to split energy between two. So the ratio is 1.5 cells to one bulb, which is more than the ratio of circuit A's 1:1. So that means in this circuit, the lamp will be brighter than the bulb in circuit A. It may not be as bright as this circuit, but it will still be brighter than circuit A. So in year 7, you don't need to do the calculations yet. The calculations will only be covered at a higher level and will be covered in more detail in year 10 and year 11. So for now in year 7, you just need to be able to identify what happens to the lamp. Is it going to be same brightness, dimmer, or brighter? So based on this, you should be able to understand this is why sometimes some lamps or light bulbs may burst if you supply too much energy to it. That means too many cells, or you connect in such a way that the voltage is way too high. Because if it's too bright, there's just too much energy, the lamp may not be able to accept it. That's why it bursts. Make sure that when you connect the lamp or the light bulb, you need to use the correct voltage, which is already stated on that lamp. So now when it comes to experiments, it is always much better to be able to set up the physical practical experiment in the lab. So for my students, we will definitely do this in a future lesson. If you're from another school or from another class, your teacher will also most likely be setting up an opportunity for you to do this in your school labs. If you're learning this on your own, maybe at home, or you're doing your own self-study, and you're wondering how to be able to do these electrical experiments, you should be able to get some electrical experiment kits which you can do safely at home. I do have a kit like that myself at home too, which I will cover in another video. For now though, because we're learning this online, I'd like to share with you this website where you can also explore more about electrical experiments on a website. So this is an excellent animation website by FED Colorado. Even if you're doing an actual physical practical experiment in the lab and you're struggling to understand how electrical experiments work, you can set up your experiments and refer to this website at the same time to be able to give you a deeper understanding of how electrical experiments work. So how do we use this website? It's basically a drag and drop. So on the left hand side here, you have some basic components. For example, you have a battery which you can drag over here, and you have a light bulb or a lamp. In order to make the connection, you need to have a connecting wire. So you need to make the connections at where the red circles are. So I'm going to drag the connecting wire over here, and we're going to put one more wire to close the circuit like so. And you can see now the light bulb has lit up. Let's try this with 2 cells. Okay, they call them batteries here, but you and I both know it's called a cell. Now 2 cells make a battery. Let's put a single light bulb. And you can see how much brighter this light bulb is compared to this bulb when we place 2 cells instead of 1. Now let's look at what happens if we put only 1 battery to 2 bulbs. And you can see in comparison, the light bulbs are much dimmer compared to this light bulb. So feel free to explore more with the components on the side over here. There's the resistor, the switch, the fuse. There's even other things like you can try dollar bills, paper clips, coins, erasers, pencils. So which means that you can run experiments virtually to find out whether these objects are conductors or insulators. If you'd like to see what the symbols look like, you just need to click on this icon here, which will switch it to symbol form. If you're wondering what these things are, these are actually the electrons which are moving. And if you can recall, electrons travel from negative terminal to positive terminal, opposite to the current flow direction. So this is an excellent animation that's useful not only for students in Key Stage 3, but even for Key Stage 4 and Key Stage 5. If you'd like to be able to use an ammeter, you can also put it in here. For example, if you want this to be part of the circuit, whoops, let's just move this. And you can actually read the value of the ammeter. If you'd like to set up multiple ammeters in your circuits, by all means go ahead just to find out the value of the ammeter reading. If you know how to use a voltmeter, you can put that in as well. For my year 7 students, we're not learning voltage or voltmeter just yet, and we'll be focusing only on current and the ammeter. And that is it for this video lesson. So if you found this video to be educational and helpful, do click like, subscribe, and let me know in the comments how you have found this video to have helped you. If you'd like to help me keep making free educational video lessons and lab practicals, donations are welcomed at my Ko-fi page. That's ko-fi.com/physicsrocks. If you are interested in the worksheet and would like to know how to get a copy, let me know in the comments as well. I will share updates about booklets and worksheets on my website at physicsrocks.com. Now, while you're there, do check out my other physics lessons which I have on IGCSE Physics, SPM Physics, Home Learning, and coming up soon, A-Level Physics. Free lessons are also available on my YouTube channel, so do subscribe and check out videos on other topics which you might find helpful. Happy studying!